Our last function in chapter 4 is a pretty a strange, pretty unique function, one we probably haven't commonly seen before. It's a product of two functions, okay? So it's x multiplied by 5 minus x raised to the 2/3 power. Now, the exponent 2/3 is an interesting exponent. The third root of a quantity squared, okay? So the 2/3 exponent is, okay, a lot like this. Okay, so I'd have so I could take the third root of a negative number and then square it. I'd still have a positive result here. Okay, we're going to analyze the function first. Okay, just the function first. So we're going to look at domain. Okay, and I think the domain is anything, to be quite honest. When I look at that and consider this function, I could put any value of x in here. Okay, put any value of x in here, positive value, negative value. Then I take the third root, okay, or square it, no matter what the result is. Okay, so if this was positive or negative, I square it, it'd be a positive, and then I could take the third root of it. That would be fine, and then I could multiply it by that same result. I think the domain, we'll confirm it on Desmos, but I think I can take any value here for x, and I still get a nice calculated value for y. Now similarly, a range, I think I can always get a value here. Okay, when I put it in arbitrarily values for x, I can take again the third root square, take the third root and multiply it by. I generally will get values for the range, but again, once again, we will confirm this when we graph this. Now I know in the last question we held off on making a statement about range, okay, but I think, okay, in this case, okay, we've got range values here. Before I go any further and talk about intercepts, I want to consider endpoint behavior as well. So the endpoint, okay, sort of the horizontal asymptote idea here. So the endpoint behavior requires us to take a look at, okay, these two limits. Okay, and what happens when I put in, let's do the positive infinity here. Okay, so if I put in a large positive number into my function, okay, a large positive number, I'd have a negative. Okay, take the third root of a negative, it's still a negative. Square it becomes a large positive number, multiplied by a large positive number is still infinity. Okay, the negative infinity, so I'd have a negative here, and I have a positive here, okay, because ultimately at the very end, I'm squaring a negative number here. Okay, I'm squaring a positive number. Regardless, I'm squaring it still positive multiplied by a negative. They're both very large numbers, so I'd have a negative infinity. So when these endpoints exist, and I'm going to graph this over here, let's start our graph, but when I have these endpoint situations, okay, so I have, here's an endpoint, okay, and here's my other endpoint. That's sort of what this looks like. Let's do roots, okay, before we start taking the first derivative. All right, roots. Okay, so I've got, let's do okay, our roots are x-intercepts here. Okay, so I'm going to let okay, x equals 0, and I'm going to calculate a value of y, and that would be 0. Okay, so I've got an origin. I guess that was my y-intercept first, okay? And I'm going to let y equal 0. Okay. Okay, so I've got a situation where x equals 0, that one turns up, or 5 minus x equals 0. Okay, well the only way an exponent can be 0 is when, okay, the base is 0. Okay, so I've got a couple of, okay, I've got this one here, my origin turned up here, and I've got x minus, okay, so x equals 5 here. Okay, and that'll be the point, 5 and 0. Okay, just over to my graph, point here, and a point at, say, approximately 5 and 0. All right, so we're good to go with the first derivative. Okay, now the first derivative, okay, is going to give me my critical points and my intervals of increase and decrease. Now the first derivative, I'm going to use the product rule on it. So my product rule, and I'm going to leave you guys to this, my product rule, okay, is going to be, okay, so I'm going to pause this and go and calculate my first derivative over here using my product rule. So I've got to do some calculations, and we'll get back to it real quick. And I'm also going to simplify it as well, so you guys can do that while I pause this. Okay, time to pick it up again here. Okay, so my first derivative was found by using the product rule. That work is over in this side here. It works out to be this long expression. Okay, I stopped here, set it equal to 0, and tried to factor it and work on it. So I identified in this line right here, okay, I identified a greatest common factor of 5 minus x to the negative 1/3 power, and that's what I removed. That left me with a 5 minus x to the power of 1. Okay, so when I subtract those exponents, when I divide both of these terms, okay, so this term, okay, and this term, when I divide both of those terms by 5 minus x to the negative 1/3 power, I'm left with 5 minus x to the power of 1 and a minus 2/3. Now the reason I chose to remove 5 minus x to the negative 1/3 power is because of the existence of the term right in here. That's a messy situation, especially when I multiply it by 2x over 3, and by removing that greatest common factor, it cleans up not only the first expression, becomes 5 minus x to the power of 1, but it also leaves a second expression with negative 2/3 x. And that allows me to simplify this really nicely. Okay, so now down to this stage, I now have, okay, I'm going to write this as a positive exponent, so that's going to be 1. And I'm going to put, set that equal to 0. Okay, the only way this expression can be 0 is when the two factors can equal 0. That's 5 cross multiply. All right, x equals 3. All right, so there's no solution over here. There's no way, okay, a reciprocal function, 1 over some expression is going to give me 0. Okay, even if I put 5 in here, if I put 5 in here, I get 0 in my denominator. Okay, so that would be something I couldn't calculate. So there's no solution in here. So they don't exist in this area. But there's something important about, okay, 5, and it's going to turn up here, and I want to talk about it in a minute after I deal with this one. The second place I get a 0 is when x equals 3. Now, I did the math here quickly. That was the point 3, and I think I have it written down, 3 and about 4.76. Now, the way I got that y value is I put x equals 3 and back into my original function. I'll let you guys do that. But I want to identify the fact that my first derivative turns up 2 critical points, okay? And that's because of this right here, okay? So I know I didn't get an x equals 5 here, okay? But I want to talk about x equals 5 now. So, and in this expression, okay, I'm dividing by, okay, this root. So, okay, this root 5 minus x, okay, and x equals 3 are points I want to check. This one's a critical point, okay, that I want to check. I'm going to call this one, for lack of a better word, just an important point here. It's a value on my function, okay, that should be looked at in greater detail. It exists in here, in this area. There's something going on. It could very well be an asymptote, okay, but it might be something a little bit more than that. Okay, now again, remember, it turns up in the first derivative check, so it has to do with slopes of the tangents. Okay, now did it turn up here? Yeah, it turned up as a root as well. Okay, so not only is it a root, but it's a place where our first derivative does not exist. Okay, so let's put this into a sign chart here. Okay, so I've got, okay, when x is less than 3, I've got when x is between 5 and 3, and then when x is greater than 5. And I'm going to do my first derivative, and my first derivative expression is going to be, okay, this one right here, okay, one of the bottom ones. Okay, so I'm going to have okay, so I can use 0, I can use 4, and I can use 6 here. All right, let's see if we can get this changed to red just to highlight it here. Okay, when x equals 0, I've got a positive, right? 0, if I put a 0 in here, okay, I've got a positive. If I put a 0 in here, I've got a positive. Okay, so the result of a product of a positive and a positive are positive. Okay, so this is increasing. Okay, when x equals 4, I've got a positive, okay, and I've also got a, okay, 20 over 3. Okay, that sounds like it's a negative here. Okay, so it'd be a positive times a negative. Okay, would be a negative, so I've got a decreasing interval. Okay, and then okay, when x is greater than 5, so for a value of that, it would be x equals 6. I've got a negative. A radical expression is a negative, and I've got a negative in here, and a negative is positive, and that would mean it's an increasing interval here. All right, so I'm going from increasing to decreasing, okay, to increasing again. So let's see if I can show that on my graph. Okay, so I was increasing. If this was 5, this would be about 3. So I'm increasing. Okay, up to 4.67? 4.76. Okay, and then I'm decreasing, and then I'm increasing. Okay, all right. That's in fact our graph, and I'm going to show this in Desmos, okay, but I want to do the second derivative. So I'm going to get this set up in Desmos, okay, and see that we've got, okay, that represented, okay, this situation here, okay, represented, okay, in Desmos. And I want to do the second derivative, talk about the important part of the second derivative here. All right, here's our function in Desmos, and it is exactly what we thought it was. Our sketch is pretty close to this particular function. There's going to be an important point that turns up in the second derivative, though, that we're going to spend the rest of this video focusing on. Okay, so here we've got increasing all the way up to 3, okay, then decreasing, and then up to 5, and then beyond 5, it's increasing function here. You can see the endpoints, okay, tend to negative infinity on this side, positive infinity on this side, okay, and that looks like it. This point at 5 is actually a cusp point, okay, that shows up. Okay, we've talked about that cusp point. Remember what I said about the derivative function, okay, not existing at the point 5, but it is a root, okay, and that's kind of how that shows up here. I want to take a minute and do the second derivative, though, and that's really worth talking about. Okay, it's going to, okay, take a little bit of time to focus on the second derivative, okay, from this particular function here, and I'm going to do product rule, okay, again on this function, okay, and see if we can find the second derivative. I'm going to pause my video, okay, and do, okay, second derivative. Before I pause it, I'm going to talk about second derivative. Quotient rule, let's do the quotient rule. And I'm going to have my first derivative function. I'm just going to rewrite that. So try it and see, and we'll be back in a minute. Okay, so here's the second derivative here, and this gets an incredibly complicated function. Um, we use the quotient rule, okay, on the second derivative. The full quotient rule is here. I focus then on just the numerator, since that was the second derivative was equal to 0, in order to find inflection points. And I worked through all this, identified a greatest common factor, wrote my second derivative, part of my second derivative function, part that equals 0. I wrote that out, factored, and got some interesting points here that didn't show up on, didn't necessarily show up on my curve. Okay, so I've got, okay, x is less than 5. So my second derivative, okay, when x is less than 5, I could choose a point here, a point that's just less than 5. Okay, why not choose 0? Okay, because that arbitrary point in this interval x is less than 5 can be any point in here. So when I actually do, okay, that I'm going to put it in this part here. Okay, so that would be the third root of 5 is positive, squared is positive, and multiplied by 1/3 would be a positive. Okay. And when x was 0, I put it over here, I'd have a negative, be negative 20. Okay, so the result here is a negative, so it's decreasing. Oh, it's not decreasing, it's concave down in that interval. Okay, the next one, we're going to use x equals 4. Be somewhere, some point between 5 and 6. Well, if I put it in here, okay, a 4 in here, so 5 minus 4 is 1, squared is positive, third root is positive, it's always going to be positive. If I put 4 in here, I'm going to have, okay, so 40 over 3, okay, plus, okay, negative 20, that will be a negative result, okay, so I still have, okay, between 5 and 6, I still have, okay, concave, I think, let me just see here, just let me double check that again. Okay, so 40 over 3, okay, take away 20, okay, is still a negative result, it's a negative result. Okay, so the product here is negative, so I've got concave down in that interval. And when x is greater than 6, so that would be like a point like 7 here. Okay, so I've got a positive. Okay, so if I put 7 in here, I've got third root squared of positive. But then I've got a positive here, and the product is going to give me concave up. Okay, so I've got to go back to my graph and see that, because I certainly didn't see that on my sketch. And I don't think I saw that on Desmos. So let's take a look and see, okay, what we've got here. But I should do this. What's the point when x equals 6 here? Okay, I'm going to put that back into my original function. Okay, that would be y equals, okay, 6, and then 5 minus 6 raised to the 2/3 power. I think that was what it was. Okay, so that would be 5 minus 6 is negative 1. Third root of negative 1 is negative 1. Squared is 1 times 6 would be the 0.66. Okay, so I have this, okay, inflection point at the 0.66. So I've gone from concave down to concave up. But again, that's worth looking at in Desmos and seeing that is in fact what we've got here. Okay, so here's our graph in Desmos again. And we found on our sign chart of our second derivative, we found that between, okay, less than 5, so that's this interval in here. Okay, so less than 5. Okay, so less than 5 is concave down. Okay, and then I've also got between 5 and 6. I've got a concave down situation in here. Okay, I wonder if I can get. Not necessarily here. Okay, all right. So between 5 and 6, I've got a concave down situation, and then from 6 and beyond, I've got a concave up. So the graph really sort of bends. It bends in here, and I don't think I can even if I zoom in quite a bit. I don't think I can see that. Okay, quite, you have the 0.66 here. So at this point here, I certainly don't think I could, okay, see that on my function here. I can even try, okay, to adjust it. So between, let's go between 4 and 7. Okay, I have a step pattern of like even like 0.1. Okay, and I go between 4 and 7 as well. Still don't. Okay, I still don't see that. There's the cusp point pretty clearly, but at 6, can I even see that? That bend here, there's my 0.66. I can't at all. Okay, it shows up when I do it algebraically, but it certainly doesn't show up, okay, when I do this, okay, graphically. So it's worth taking a look at and understanding just the scope of that function, okay, and handling it algebraically. So that's it for chapter 4. Hope you guys work away on the review assignment and get that handed in when you're done. Thank you.